Testing, testing. One, two, three. Hopefully it works. Let me see if it's going to work. Hello. How's it going? Okay, good. All right. So welcome back to our stream. So today we're gonna continue working on um, the textbook, the introduction of number theory. Or full name, the friendly introduction to number theory, and again, by the author. His name is once again uh, Joseph Silverman. And last time we ended in chapter 3. So this is where we are at last time. So last time we were almost done with chapter 3. Chapter 3 has uh, again chapter 3 is the Pythagorean triples and the unit circle, and we actually got 5 problems. Yeah, and the last time we finished the first 4 already, so we have only the last problem remaining, the problem 5. Uh, and here is the question. Numbers that are both square and triangular numbers were introduced in chapter 1, and you study them in exercise 1.1. Again, we all know what square numbers are, meaning that is a number that can be written as some integer times itself. And what is a triangular number? Well, a triangular number is geometrically, if we try to start from 1 and then plus 2 plus 3, so on and so on, up to n. And then if a number is actually a sum of such uh, finite sequence, then we will say that is a triangular number. And again, for example, we have uh, the first triangular number is 1, which is just equal to 1 itself, where the next one is 3, which is actually equal to 1 plus 2. And then after that, it will be 6, which is equal to 1 plus 2 plus 3. And then we have 10, which is equal to 1 plus 2 plus 3 plus 4. And then next one will be 5 more than the previous one, and then 6 more than the previous one, so on and so forth. Okay. And of course, generally speaking, we the nth triangular numbers will be equal to 1/2 times n times the quantity n plus 1, or also known as 1/2 equals n squared plus n. Okay. Um, so this time we have 6 parts, and we're going to solve all of them and finish this chapter. So part A shows that every square triangular number can be described in using the solutions in positive integers to the equation x squared minus 2y squared equals 1. Hence, rearrange the equation m squared equals 1/2 quantity n squared plus n. And again, that is saying that if a number is a square triangular number, it is a square number and a triangular number simultaneously. And therefore, we can try to rewrite such number. Let's call it some number a. Okay, we can write it as m squared, where of course m is an integer, but also be written as 1/2 times the quantity n squared plus 1 plus n, where in this case n is also an integer or positive integer in this case, we're assuming. Then because it actually satisfies both properties, we can just set a to be equal to um, a square as well as a triangle number. That's why we use the hint that we have. So how do we do it? Well, we're going to do some scratch work here, of course. And again, we're trying to uh, we're trying to uh, get some uh, scratch word, just like how we usually write proof. We if we don't know how the intermediate steps work, we can just try to reverse the engineer by basically trying to or try to set us up something and see if we can actually get the results we need. So here is a scratch word, by the way. I'm gonna put something in a sketch. Okay, so in this sketch, we'll just start with the equations in the hint. Okay, so we see that in this equation we have m squared is equal to 1/2 times the quantity n squared plus n. Of course, we're doing a scratch word so far, so don't worry about the detail of such as you know naming that m and n are integers, whatever. We know what they are for now. We're just trying to get a big picture for now. So now we need to rearrange this equation or manipulate the algebra. So first we can try to let's see. We can for now try to multiply both sides by 2, of course, trying to get out the factor, right? So we will actually end up with 2m squared is equal to the quantity n squared plus n. Well, this is clear enough because we're just basically trying to set up something very nice. Then what will be next? Because our goal is to get the form x squared minus 2y squared, okay, on the left hand side. So let's try to throw the 2m squared to the right side and then put everything to the left, okay, which means that we now will end up with the following: n squared plus n, and then minus 2m squared is going to be equal to 0, of course. Oops, we don't need two equal signs. Okay, so this is what we're going to have. Now, clearly, in this case, we kind of have the y ready. Okay, we have the y, sort of having the y ready in this case. But then the x part doesn't look nice. Besides, we have we have n squared plus n, right? When in order to get a perfect square, we need to complete the square. But if we try to complete the square with just n squared plus n, here is the problem. We have the square term, we have the linear term, but then if we try to add the constant term to this part so that we can complete the square, what we need will be the following. So we actually will need to get something like let's see if I can actually color code it. Color. This is plus then minus. Now, anyway, the biggest problem that we have here, which we are going to show in the coloring, is that hopefully it works. Let's see if it's going to work, though. I'm not sure. This is okay. It doesn't work. But anyway, I'm gonna uncolor code it. We don't really need this part. Because I mean, you are smart. You should be able to tell what has been changed between the two lines. Okay. So what we did is we added what's so called a fancy zero, right? But then for this fancy zero, or maybe I can just put parentheses to to specify what we actually not. So this is what we add, which is everything inside parentheses, which is adding the 1/4 and then subtracting back a quarter, which means again we're going to add a fancy zero. There's nothing changing on the left side of the equation. Okay. Now the thing that we're doing is that we're trying to add this so that now as we break it into two parts and rearrange in the left side, we actually will be able to get something like this. So I'm going to put the 1/4 and attaching with the n squared plus n. So we are going to get something like this. And then for now, don't worry about the rest. We still, of course, need to write down the rest. Minus a quarter, and then minus 2m squared, which is equal to 0. Okay. Now, why do we do that? Because now once we see what we have inside the parentheses, those three terms will actually form a perfect square, which is actually equal to n plus 1/4 or 1/2 quantity squared. However, this actually gives us the problem that everything inside of the parentheses is no longer an integer because n is an integer, and a half of it, an integer plus a half, will actually be saying that an integer plus 0.5. So we'll end up with something 0.5. Okay, it's definitely not an integer, and this is actually not what we really want because again, our goal is to make this part inside of the parentheses to form as an integer so that it will look very close to x squared in our goal. Okay, but we cannot have an integer inside if we actually get a quarter. If we actually add a quarter, so how can we avoid this? Well, let's go back to a few steps ago. We know this that in this case, if we try to add a fancy zero, we need to add 1/4, a fraction. So if we go back to this part, in order to get rid of the fraction, we might as well just multiply both sides of the equation by quarter, right? The common denominator, so that everything will actually turn back into an integer. So in other words, we can actually try to start off with multiplying both sides by 4. No, back to the fourth line. So instead of having just n squared plus n minus 2m squared equals 0, we're going to multiply everything by 4 in this case, so that it turns out to be 4n squared minus 4n minus 8m squared equals 0. Okay, and here comes the magic. Sometimes when we try to solve an equation, of course, we're trying to try to get rid of all the common factors out that are non-zero. Okay, non-zero constant in this case, to try to reduce it and trying to minimize our work or make it less complicated when we try to do the fractions. But when we are dealing with something like this, like trying to play around in number theory, we actually need to do the other way around sometimes because our goal is to keep everything in as an integer, uh, so that it will be easier to satisfy the conditions that we need. Now, after this, now we can actually add the fancy zero, which in this case we can call it 1 minus 1. Okay, so this is what we get, 1 minus 1. So we actually get our goal here. So that now if we try to